Welcome back. In this chapter, we'll focus on the core engineering concepts used to design efficient, scalable networks. You'll learn how Layer 2 technologies and the TCP/IP model work together to improve performance, security, and manageability. You will explore how to segment a flat network into smaller broadcast domains using VLANs, improving efficiency and reducing unnecessary traffic. This includes understanding VLAN types, valid ranges, and how to configure VLANs, trunks, and inter-VLAN routing for end-to-end connectivity. You'll also learn how to map and understand network topologies using Layer 2 discovery protocols such as CDP and LLDP, and how to increase bandwidth and redundancy between switches by bundling multiple links using EtherChannel. These are the topics covered: VLAN fundamentals and VLAN types, VLAN and trunk configuration, inter-VLAN routing, Layer 2 discovery protocols, and EtherChannel concepts and configuration. As networks grow, more devices and applications share the same physical infrastructure. In a flat Layer 2 network, all devices belong to a single broadcast domain, meaning every broadcast frame is received and processed by every device. As the number of devices increases, excessive broadcast traffic can lead to congestion, wasted processing resources, and degraded network performance similar to traffic congestion during peak hours on a busy road. Organizations commonly face questions such as, how can unnecessary broadcast traffic be reduced? How can overall network performance be improved? How can voice, video, and data traffic be separated without buying new hardware? And how can users with similar roles be logically grouped on the network? The solution to these challenges is the Virtual LAN Area Network. A VLAN is a logical Layer 2 network that segments a physical network into smaller broadcast domains. Instead of relying on routers for physical separation, VLANs allow logical segmentation using switch software. This reduces broadcast traffic, improves performance, and enhances security. In a traditional flat network, a Layer 2 broadcast is forwarded out all switch ports within the same broadcast domain. Routers stop Layer 2 broadcasts, creating separate broadcast domains per interface. VLANs achieve similar segmentation logically without additional routing hardware. Key concepts: each switch port is a collision domain. Each router interface is both a collision domain and a broadcast domain, and VLANs divide a single physical network into multiple logical broadcast domains. Each VLAN must be assigned a unique IP subnet, since devices still require IP addressing to communicate. Switch ports assigned to end devices are called access ports, and each access port belongs to a single VLAN, except when using a separate voice VLAN alongside a data VLAN. When traffic enters a switch on an access port, it is internally tagged with a 802.1q VLAN ID, which identifies the VLAN to which the frame belongs. This tagging allows switches to keep VLAN traffic logically separated, even while sharing the same physical infrastructure. Before frames leave an access port, the VLAN tag is removed, as end devices are unaware of VLAN information. So the basic VLAN configuration on a Cisco IOS: create a VLAN and assign a name, and remove a VLAN using the negated form of the command no VLAN and the ID. By default, VLANs cannot communicate with each other. Communication between VLANs require inter-VLAN routing, typically performed by a router or a Layer 3 switch. The benefits of VLANs include reduced costs, improved performance, enhanced security, and improved IT efficiency and management. Overall, VLANs transform a flat Layer 2 network into a structured, scalable, and secure network design while maximizing the use of existing infrastructure. VLANs are identified by numeric VLAN IDs, and Cisco switches support two VLAN ranges: normal range and extended range. VLAN IDs range from 1 to 1005. VLANs 1002 to 1005 are reserved for legacy Layer 2 technologies, such as token ring and FDDI. VLAN 1 and VLANs 1002 to 1005 are created automatically and cannot be deleted. VLAN information is stored in the VLAN.dat file located in flash memory. When factory resetting a switch, the VLAN.dat file must be deleted to remove VLAN configurations. So here we have the extended range VLANs. VLAN IDs range from 1006 to 4094. VLAN configurations are not stored in VLAN.dat. Configuration is stored in the running config by default, and fewer features are supported compared to normal range VLANs. With an understanding of VLAN ranges, we can now explore the different types of VLANs used in enterprise networks. There are 5 VLAN types used on Cisco switches, each serving a specific purpose in an enterprise network. A default LAN. When a Cisco IOS switch is first powered on, it works without any configuration because all ports are assigned to the default LAN. The key characteristics: default VLAN is VLAN 1. All switch ports are assigned to VLAN 1 by default. VLAN 1 is the default management VLAN. VLAN 1 is the default native VLAN. And VLAN 1 cannot be renamed. Best practice: VLAN 1 should not be used for user or management traffic due to security risks. Number 2. Data VLAN. A data VLAN is used to carry regular user traffic, like PC, servers, printers, etc. These VLANs are assigned to switcher access ports. Key points: only one data VLAN can be assigned per access port, all inbound traffic is tagged internally with its VLAN ID, and it's suitable for all data frame types. Basic access VLAN configuration: set interface to access mode and assign the VLAN ID to the interface. Interfaces can be reset using the negated form of the original commands. Number 3. Voice VLAN. A voice VLAN is dedicated to VoIP traffic and keeps voice packets separate from data traffic to improve call quality. The key points: improves VoIP performance and reliability, allows 2 VLANs on one interface, 1 data VLAN and 1 voice VLAN, and is commonly used with IP phones. This is the only exception where 2 VLANs are allowed on a single access port. Number 4, you have management VLAN. The management VLAN is used to remotely manage the switch. The key points: implemented using a switch virtual interface, assigned an IP address and subnet mask, used for remote access via SSH, HTTPS, Telnet or HTTP, and should be a separate subnet from other VLANs. Best practice: never combine the management VLAN with user or data VLANs. And last but not least, number 5, native VLAN. The native VLAN carries untagged traffic across an IEEE 802.1q trunk link. The key points: used for traffic generated by network devices. Default native VLAN is VLAN 1. Can be changed for security and design reasons, and must match on both ends of a trunk. An important note: a native VLAN mismatch on trunk links will cause connectivity issues. With VLAN types understood, the next step is learning how trunk links allow multiple VLANs to span the entire network. Trunk interfaces are used to carry multiple VLANs over a single physical link, typically between switches or between a switch and a router. This solves the limitation of access ports, which can carry traffic for only one VLAN. When 2 switches are connected using an access link, only the VLAN assigned to that link can pass between them. For example, if the link is assigned to VLAN 12, devices in VLAN 10 can communicate across switches, but traffic from VLAN 20 or any other VLAN is blocked. Key concept: switch-to-switch links are trunks, switch-to-router links are also trunks. By converting the link to a trunk, multiple VLANs such as VLAN 10 and VLAN 20 can traverse the same physical connection simultaneously, allowing devices in different VLANs on different switches to communicate end-to-end. Here's a trunk configuration on Cisco IOS. A trunk interface is configured as follows. Set the interface to trunk mode, specify which VLANs are allowed on the trunk, optionally configure a native VLAN, and enable the interface. Right, here's a breakdown of trunk configuration. Encapsulation. Some older Cisco switches require specifying .1q encapsulation before enabling trunking. Modern switches use IEEE 802.1q by default. ISL is a deprecated Cisco proprietary protocol. Switch port mode trunk. Forces the interface into trunk mode. Switch port trunk allowed VLAN. Defines which VLANs are permitted across the trunk. Switch port trunk native VLAN sets the VLAN used for untagged traffic on the trunk. And then we have removing configurations. So no switch port trunk allowed VLAN removes the VLAN allow list. No switch port trunk native VLAN resets the native VLAN to default. Here's a quick summary. Access ports can carry one VLAN. Trunk ports carry multiple VLANs. Trunks are essential for scaling VLANs across multiple switches, and native VLANs must match on both ends of a trunk to avoid connectivity issues. With trunking understood, the next topic is dynamic trunking protocol, which allows Cisco switches to automatically negotiate trunk links. So DTP, dynamic trunking protocol. Cisco switch ports can operate as access ports or trunk ports, but they can also negotiate their role with neighboring switches. This negotiation is handled by dynamic trunking protocol. DTP is enabled by default on Cisco iOS switches, with interfaces set to dynamic auto mode. DTP interface modes. So you've got switch port mode access, forces the interface to remain a non-trunking access port. Switch port mode dynamic auto, passively waits for the neighboring interface to request trunking. Switch port mode dynamic desirable, actively attempts to form a trunk link with the neighboring interface. And switch port mode trunk. This forces the interface into permanent trunk mode. Disabling DTP negotiation. The switch port non-negotiate command prevents the interface from sending DTP frames. The key points: interface comes up faster, can be used only on statically configured access or trunk ports, and neighboring interface must be manually configured to match. Verifying DTP status. Show DTP interface and the interface ID. This displays the current DTP mode. And show interface. The interface ID switch port shows administrative mode, optional mode, and DTP status. DTP negotiation behavior. Two switches using dynamic auto, access link, dynamic desirable connected to dynamic auto, trunk link, and trunk mode connected to any trunk capable mode, trunk link. Understanding DTP is essential to avoid unattended trunk links and to apply secure, predictable network designs. Next, you will learn how Inter-VLAN Routing enables communication between devices on different VLANs. Inter-VLAN Routing allows devices on different VLANs to communicate with each other. Since VLANs are separate Layer 2 broadcast domains, a Layer 3 device is required to route traffic between them. The most common method used today is router on a stick, which enables a single physical router interface to support multiple VLANs by using sub-interfaces. Why router on a stick? Normally, each router interface connects to a single subnet and acts as that subnet's default gateway. In a network with multiple VLANs, each with its own subnet, this would require one physical router interface per VLAN, an expensive and impractical solution. Router on a stick solves this by using one physical router interface, creating multiple logical sub-interfaces, assigning one VLAN and one default gateway IP to each sub-interface, and connecting the router to the switch using a trunk link. How traffic flows between VLANs. When a device in one VLAN communicates with a device in another VLAN, the source device detects the destination is on a different subnet, traffic is sent to the default gateway, the switch tags the frame with the source VLAN ID, the router receives the frame on the matching sub-interface, the router performs a Layer 3 routing decision, traffic exits the router through the destination VLAN sub-interface, and the switch removes the VLAN tag and forwards the frame to the destination device. So here we got sub-interface configuration. Basic steps to configure router on a stick. Create a sub-interface on the network. Associate it with a VLAN ID using 802.1q encapsulation. Assign the default gateway IP address and enable the physical interface. Each sub-interface represents one VLAN and one IP subnet. Enabling the physical interface no shutdown automatically enables all configured sub-interfaces. The key takeaways: VLANs cannot communicate by default. Inter-VLAN routing enables communication between VLANs. Router on a stick is cost-effective and scalable. Each VLAN requires a unique subnet and a router sub-interface acting as its default gateway, and the router switch link must be a trunk. With Inter-VLAN Routing understood, you're now ready to move into hands-on VLAN implementation and configuration. Layer 2 discovery protocols allow network engineers to identify and map a network topology without relying on physical diagrams. These protocols enable you to discover information about directly connected neighbor devices, making troubleshooting and documentation much easier. By By using Layer 2 discovery protocols, you can determine neighbor device roles and capabilities, connected local and remote interfaces, device model information, management IP addresses, and overall network topology and device relationships. In this section, we will focus on two widely used Layer 2 discovery protocols and learn how they help visualize and understand a network from the command line. Cisco Discovery Protocol is a Cisco proprietary Layer 2 protocol used by Cisco devices to discover information about directly connected neighbors, such as switches and routers. CDP is enabled by default on Cisco iOS switches and routers. Devices exchange CDP advertisements using the multicast MAC address. Information shared by CDP. Each CDP message includes key device details such as iOS version, device model and type, local and remote interface information, and hostname. This allows network engineers to quickly identify connected devices and understand how they are interconnected. The CDP configuration: enable CDP globally, CDP run, disable CDP globally, no CDP run, enable CDP on a specific interface, CDP enable. Here's some security considerations. Because CDP advertises detailed device information, it presents a security risk if captured by unauthorized users. Best practice is to disable CDP on interfaces connected to end devices and allow CDP only between trusted switches and routers. Verifying CDP neighbors. Show CDP neighbors, displays directly connected devices, their roles, models, and interface connections. Show CDP neighbors detail, provides additional information including IP addresses. Show CDP interface, and then the interface ID displays CDP timer settings per interface. CDP timers. CDP advertisements are sent every 60 seconds. Default hold time is 180 seconds, and neighbors are removed from the CDP database if updates are not received within the hold time. The limitations of CDP. CDP works only on Cisco devices, which limits its usefulness in multi-vendor environments. The next section introduces Link Layer Discovery Protocol, an industry-standard alternative. Link Layer Discovery Protocol is a Layer 2 discovery protocol used to identify directly connected neighbor devices. Unlike CDP, LLDP is vendor neutral, making it suitable for mixed vendors enterprise networks. LLDP is defined by IEEE 802.1ab, which ensures interoperability across Cisco and non-Cisco devices. On Cisco iOS devices, LLDP is disabled by default and must be manually enabled. So why use LLDP? It works across multiple hardware vendors, industry standard discovery protocol, ideal replacement for CDP in enterprise environments, and enables accurate network topology mapping. LLDP configuration on a Cisco iOS. Enable LLDP globally, that would be LLDP run. Enable LLDP on an interface. Enable LLDP reception. Enable LLDP transmission. Both receive and transmit must be enabled for neighbor discovery. Verifying the LLDP operation. Show LLDP. This displays global LLDP status. Show LLDP neighbors. Shows directly connected LLDP enabled devices. Show LLDP neighbors detail. Provides detailed neighbor information including IP addresses. Summary: LLDP overcomes the main limitation of CDP by supporting interoperability across vendors, making it the preferred discovery protocol in modern enterprise networks. Using CDP or LLDP outputs, network engineers can easily build and maintain accurate, up-to-date network diagrams. Next, you will learn how to increase bandwidth and redundancy by bundling multiple switch interfaces into a single logical link using EtherChannel. When connecting two switches using multiple physical links, the goal is often to increase bandwidth and provide redundancy. Simply plugging in multiple cables does not achieve this automatically, because spanning tree protocol prevents layer 2 loops by blocking redundant links. An EtherChannel solves this problem by bundling multiple physical interfaces into a single logical interface, allowing all links to be used simultaneously while STP treats them as one connection. Cisco calls this technology EtherChannel. Other vendors refer to it as link aggregation group. The benefits of EtherChannel: it combines bandwidth from multiple links into one logical interface. It prevents STP from blocking redundant links, simplifies configuration by applying settings to the port channel instead of individual ports, provides load balancing and redundancy, and uses existing switch interfaces. No extra hardware required. EtherChannel requirements: all member interfaces must match on both switches. So the same interface type, same number of interfaces on each side, same speed and duplex settings, same VLANs and native VLAN, and same trunking configuration. If any settings differ, the EtherChannel will not form. EtherChannel protocols: Cisco supports two layer 2 EtherChannel protocols. You have PAGP, this is Cisco proprietary, the modes on, desirable, and auto, and you have LACP. The modes are on, active, and passive. LACP is the preferred and recommended standard, especially in multi-vendor networks. EtherChannel configuration using LACP. High-level steps: number 1, shut down the physical interfaces to prevent loops. 2, group interfaces into a channel group using LACP. 3, enable the interfaces. 4, configure the logical port channel interface. And 5, verify EtherChannel status. Here's some of the key commands. So verification: show EtherChannel summary, confirms EtherChannel creation, protocol used, and active interfaces. Show EtherChannel port channel, displays detailed EtherChannel configuration and status. The key takeaways: STP blocks redundant physical links by default. EtherChannel allows multiple links to function as one logical link. All interface settings must match exactly. LACP is the industry standard and preferred protocol, and EtherChannels improve bandwidth, redundancy, and scalability. So in this chapter, you learned how to segment networks using VLANs for performance and security, configure access port, trunk ports, and inter-VLAN routing, discover network topologies using CDP and LLDP, and aggregate physical links into a single logical interface using EtherChannel. In Chapter 6, you will dive deeper into loop prevention, redundancy, and advanced Layer 2 network design concepts in preparation for the CCNA exam. That brings us to the end of this chapter. Thanks for sticking with me and working through VLANs, discovery protocols, and EtherChannels. I really appreciate everyone who subscribed and continues to support the channel. It genuinely means a lot. If this helped you, make sure you're subscribed so you don't miss the next chapter, where we'll dive into spanning tree protocol. Thanks again for watching. I'm CyberEd, and I'll see you in the next one. Peace.